Let's address complex exponents. Okay, to the notes for section 3.33, complex exponents. And we're kind of motivated by the way things behave in the real setting. You know what it means to raise a real number to a natural number power. It just means repeated multiplication. Cubing a number is multiplying it by itself 3 times. Negative natural numbers, raising a number to the -3 means taking the multiplicative inverse and cubing that. Rational exponents, say raising a number to the 2/3 power, means first squaring it and then taking cube roots in the real setting. But what's it mean to raise a real number to an irrational power? And you went through this in calculus too, and the way you defined it was in terms of the natural log function. Surprisingly, that's what the equipment it takes to define raising real numbers to irrational powers. So complex numbers, it's going to be dealt with rather in a similar way. We're going to use log functions to define what it means to raise numbers to a complex power. Of course, the problem with that is the log function's periodic. We've been dealing with this multiple valued stuff, and that'll arise in the setting here as well. So the plan is to base raising numbers to complex powers on logarithms, branches of the logarithms. Multiple valued stuff will come to bug us again. So first, we'll define for non-zero complex number z, the multiple valued function z to the c, where c is a complex number, as z to the c equals e to the c log z. Here, this log z denotes the multiple valued log function that we dealt with in the past, telling you then this z to the c thing is potentially also a multiple valued function as well. And as I just commented, we're really following the protocol that you do in calculus too. When you define a to the x and log base a, everything's done in terms of natural logs, ultimately in natural exponentials. And even in calculus, it's built up from there. So what we're doing here is quite similar to that. So let's take that definition and let's calculate I to the -2i power. Okay, well, by definition, this would be, peek back at the definition since I made the fonts large, we've got I to the 2i power, so it'd be an exponential function with the exponent c and the log of the base. Okay, we wanted I to the -2i. We'll have an exponential function. Here's the exponent, log of the base, log of the I. Okay, now it's just a matter of unwinding the meaning of this. Log of I, the multiple valued deal in terms of lowercase a argument, lowercase l log, is the log of the modulus of I plus I times this argument stuff. I has modulus 1, log of 1 is 0, so we lose that. And argument, the principal argument of I is pi halves, so we can take that and then just add multiples of 2i pi, let n be an integer, and we'll take care of it as given here. Okay, so here's the log part that we get. So we'll substitute that in the exponential function. And we'll have the exponential function, -2 pi I, replace the log stuff with this stuff, n's an integer, so we're getting lots of things out potentially. Substituting n, funny thing happens, geez, the I from here and the I from here get together, produce a -1. We lose this negative sign here, and we're left with e to the 2 times pi halves plus 2n pi. We'll distribute that 2, and we'll get e to the pi plus 4n pi. I could factor the pi out if you like. That's real. So that's a little weird. And it ranges over the integers. So what we've produced here for I to the negative 2i power is a bunch of different real numbers. Actually, there's infinitely many of these real numbers. And we've got a function, multiple valued function, big time multiple valued. It takes on an infinite number of values. The surprises, they're all real. Maybe you didn't quite see that coming. I'm sure this is argument's fault somehow or other. And you see argument, yeah, there it is. It's buried inside that log stuff. And these exponential type things are defined in terms of logs. So I'm not surprised that we didn't get a bunch of different answers. A little surprised they're all real in this particular setting, but there's the computation. All right, just as we had a principal value and a principal branch of the logarithm, we're going to have branches and principal branches of this z to the c function. So let lowercase l log z represent some branch of the logarithm. I got a good deal of respect for Brown and Churchill, but they've used this same symbol, this log thing, for the multiple valued log and for branches of logs. So that's a little clunky. So you have to keep an eye on how they've worded things. So now we're talking about a branch of the log. Don't get me wrong, I'm happy we're talking about a single valued function in this definition at least. Specifically, we're talking about log z equals natural log of the modulus of z plus I theta, where we choose the argument theta to be in some particular range of width 2 pi. Between alpha and alpha plus 2 pi. In a section or two back, we went through what that means, even geometrically. It means a branch cut, for one thing. So this function is not defined for complex numbers whose argument equals alpha or is coterminal with alpha. So with this branch of the log, define a branch of z to the c as given by z to the c equals e to the c log z. This isn't exactly what we said above because now log represents a specific branch of the log instead of that multiple valued function stuff. We could choose the principal branch of the log and use it to define the principal branch of z to the c. Principal branch of the log was based on choosing arguments between negative pi and pi, excluding the endpoints for analytic reasons, for differentiability reasons, and continuity reasons. So the branch of z to the c is simply z to the c, e to the c, capital L log of z, principal branch of the log. And this is just totally consistent with the way you did it in Calculus 2. The principal branch of z to the c gives the principal values of z to the c. Brown and Churchill denote this. It's a little clunky. PV, principal value, z to the c. It produces then a single valued function, at least. Now we can finally talk about square root function. We've talked square roots, but we haven't talked square root function yet. So we're getting there. Speaking of square roots, let's look into the square root of 9 thing again. Of course, the square root of 9 is 3. It's not plus or minus 3. If you want plus or minus 3, and it could well be in applications that you do, you got to ask for it. Plus or minus the square root of 9 is plus or minus 3. The square root of 9 is 3. Now, how that relates to this is a story about branches. In the real setting, there's two branches of the square root function. There's, I'll say, positive square roots and negative square roots, and then I'll leave 0 to take care of himself. Probably should say non-positive and non-negative. But we have two choices for the value of the square root of 9, and the meaning of the symbol is to choose the positive one. Yeah, we are going to have two choices in here for square roots as well, and they'll differ by a multiple of -1. I can't talk positive and negative in the complex setting. I can talk positive and negative real parts or positive and negative imaginary parts, but I can't talk positive complex numbers and negative complex numbers. But we'll still have two choices for a square root. Okay, we'll have a principal square root and then another square root. We'll have a principal cube root and then there'll be two other cube roots for specific numbers. If we go through and actually compute the principal value of 9 to the 1/2 using all this complex stuff, that would be, by definition, e to the 1/2, principal branch of the log of the base, principal branch of log 9. All right, that principal branch of the log is defined as the natural log of the modulus of 9 plus I times the argument of 9. 9's real, its argument is 0, its principal argument is 0. So we'll lose this. We'll be dealing with e to the 1/2 natural log of 9. Gotta love that because everything in sight's real. The real exponential function and the real natural log function can be combined just to composition of inverse functions to produce the 9. 9 to the 1/2, we're totally in the real realm now. That is, the square root of 9 is 3. And even in here, the square root of 9, okay, the principal value of the square root of 9 is positive 3, not negative 3. So that kind of globally resolves this stuff about square roots and square root functions. There's two choices. We could choose a principal value of a square root function, and then there's these other values floating around out there as well, as will be the case whenever we look at z to the c. That's just an illustration where c equals 1/2. The theorem here claims that we can differentiate z to the c as defined above and get c z to the c minus 1, bring the exponent down, subtract 1 from the exponent. That sure rings a bell. We have established it in here for that exponent and integer. I think that's all we've done so far in terms of establishing this relationship. So this is new because c could be any complex number. The claim is we're doing this computation where we've chosen a branch of the logarithm to define z to the c, and we're using that same branch of the logarithm on both sides of the equation. Let's take a look at the proof. It should be no big deal. It's only cluttered up by all this branch talk. Okay, so for any branch of z to the c, we've got that the derivative with respect to z of z to the c equals cz to the c minus 1, where the branch of z to the c minus 1 is based on the same branch of the logarithm on which z to the c is based. So the little formula has anchored the conversation around a particular branch of the log. All right, well, let log z represent that branch of the logarithm that we're using. I complained about the notation a few minutes ago. Still not happy, but at least it's a single valued function. It's a regular function. Then that means log z is the natural log of the modulus of z plus I theta, where you're choosing theta according to some rule. There's some alpha, and you're taking theta to be between alpha and alpha plus 2 pi. So let's go to differentiating. Good news is you know how to differentiate exponential functions. So we should be in pretty good shape here. We know how to differentiate log functions as well. So if we take a derivative of z to the c, that is z to the c is by definition e to the c log z based on that branch of the logarithm mentioned above. Okay, well, we got a composition of functions here. Chain rule will tell us how to differentiate. You rewrite the exponential and then multiply by the derivative of the stuff inside. The derivative of c log z is c times 1 over z. We had that any branch of the logarithm has as its derivative 1 over z. Maybe a passing comment here. The differentiation formula doesn't work unless you had taken a branch of the logarithm of this type form. You can't include either of these endpoints, alpha or alpha plus 2 pi, or it's going to destroy this differentiation. So more motivation for making a branch cut and eliminating certain values of the argument. So chain rule will produce this along with our knowledge about differentiation. Z itself was written as an expression for Z itself. Here we go. I guess it was note 3.30.a. Z itself can be written as e to the log z, where we've got any branch of the logarithm and z is in the domain of that branch. So we'll make a substitution there. Now we've got a c out front. We've got a quotient of exponential functions. We know a lot about exponential functions, like when dividing, subtract exponents. So we'll manipulate that and say when dividing those exponential functions, take a difference within the exponential. So we get c e to the c log z minus log z. Let's factor c minus 1 out, leaving us with a log z. So we got c e to the c minus 1 log z. Well, that's the very definition of z to the c minus 1. We've got the exponent and the base inside a log, the pattern we had before, produces from this exponential z to the c minus 1. We've got the c out front, and sure enough, the derivative of z to the c is cz to the c minus 1. What made the story a little foggier than usual, foggier than in the real setting, is all this branch stuff. You pick a branch of the logarithm, and then you're good to go. Back to the notes. All right, let's find the principal value of I to the I. This will be another one where surprisingly we get real numbers out. I to the I, principal value. Okay, we'll use the principal branch of the logarithm, capital L log. That would be e to the I, log of the base. So this I here corresponds to the base I over here, the exponent I to the leading I in the exponential function. That was the definition. Principal value, use the principal branch of the log function. Okay, principal branch of the log is defined as the log of I plus I times the principal argument of I. I has a principal argument of pi has. It's on the positive imaginary axis, so pi has is its principal argument. We weren't using a principal branch, we were using one of those multiple valued things. We get a bunch of angles here. We're not. This is a principal value and principal logs and principal arguments. So we just get an I pi halves here. I has modulus 1, so the natural log of that is 0, and that's out of here. So we're left with e to the I times I, pi over 2, I times i's, I squared, it's negative 1. We get out e to the negative pi halves. So the value of I to the I is e to the negative pi halves. Yeah, we've evaluated the log function as pi halves, as mentioned. So another funny situation here where we get the principal value of I to the I power, imaginary numbers in the base, imaginary numbers in the exponent. They produce real numbers, and it's for the same reason that we had above. Let's look at z to the 2/3. So like I said, this is the first time we've encountered anything except for integers in exponents of functions. And then how do you feel about these functions? Well, the branches of these functions are analytic functions, and they're differentiating the way we're used to these things differentiating. So these are good functions. The multiple valued stuff I could live without, but these are good, straightforward analytic functions on their domains. Principal branch is z to the 2/3. Okay. That would be z to the 2/3. We'd take the exponential function. Here's the exponent 2/3. We'd take the principal branch of the logarithm, the base here is z, would produce this. You know how to express this principal branch of the logarithm. It's the natural log of the modulus plus I times the principal argument of that input. So let capital theta, here it says let capital theta represent the principal argument of z. Distribute the 2/3, so we get e to the 2/3, natural log mod z, plus 2/3, I times principal argument capital theta. We can split this up as a product of two exponential functions. In the first one, we'll have e to the natural log mod z. Excellent. That'll produce composition of inverse functions in the real setting. That'll just produce mod z to the 2/3 power. If you like, mod z squared, cube root of. We're in the real setting when I look at this piece of it, right? Z's complex, but its modulus is real. So we're okay there. Could z be 0? No, the log's not defined at 0. There's some other stuff it couldn't be as well. If we're using the principal branch of the log, z couldn't be a negative real number either. That's because of the principal branch of the log and its domain. It would be from negative pi to positive pi, excluding the endpoints. So there's some hidden constraints under that. Anyhow, this is a real setting, and we're okay. And then the e to the 2/3 I capital theta produces the other part. This we could expand out using Euler's formula. And here's a way to write z to the 2/3 in terms of, effectively in terms of a real part and imaginary part. It's not written in that form, but we could easily extract those from there. Definition of z to the c initially gives us this multiple valued exponential function with base c. So we could go through and define c to the z. So notice we've moved things around from z to the c to c to the z as e to the, we've got the exponent here and we've got the base inside of the multiple valued log function. And we could take branches of that, abbreviating a little bit here. But we could go through and differentiate an exponential function base c. Notice the different roles here. You're probably less familiar with this, except when c equals e. You don't deal with exponential functions in calculus much unless they're base e, because they're doing calculus. They're too messy to differentiate otherwise. You probably didn't deal with a 2 to the x function, maybe in passing. It depends how deep you went into the material. So we're approaching this in that sense. And hey, guess what happens when you differentiate this? Give me a branch or a principal branch to make sense out of the log stuff. And then what we would have similar to above is a derivative with respect to z is c to the z is c to the z times the log of that base. Hey, if that base was 1, that log would be 1, and we wouldn't have this weirdness here. But just FYI, here's how to deal with exponentials base c as opposed to exponentials base e. We are highly unlikely to ever use this stuff. You're highly unlikely in a calculus setting, and so in an analysis setting, to deal with any exponential functions other than those that are base e. Maybe out there's people living perfectly happy lives dealing with base 10 exponential functions, and a Richter scale is based on some base 10 stuff. Decibel scales are based on base 10 stuff. Yeah, they're not taking derivatives in those settings either. They take derivatives, it becomes sloppier. There's these extra factors that pop up when you differentiate exponential functions that aren't base e, that aren't natural. That's what's natural about natural exponentials and natural logs. Okay, that'll take care of that section.